Hello, Mr. Aaron, Mr. Ryan, are you alright?
Yeah.
Okay, so we talked about DAG yesterday, the graph, yeah?
Ow.
Graph, what's graph?
Hey.
What's graph?
Sorry. It's
What's graph?
E.
What's V and E?
V and E. Vertex and edges.
Vertex and edges. Okay, and what's DAG? Remember?
Directed acyclic graph.
What's acyclic?
Means doesn't go all around
Yeah,
and
it doesn't have cycle.
and round.
Can you give me an example of the DAG? Remember, what kind of data structure we have used before, we have learned before, which is the DAG? Come on, it's a tree, well done. Tree is the DAG, yeah? Why is that? Because look, root, 1, 2, 3, 4, yeah? It doesn't have arrows, but by default, you know, the parents, you can travel from parents to the kids. Yeah, there's an arrow somehow.
But can that be an acyclic?
A cycle, yeah? Look, a cyclic. Doesn't have a graph, doesn't have cycles.
Yeah, but
Directed from parents to kids.
yeah, but how would it go up again?
Good point, we don't, usually. Remember the tree node we define as this. Tree node, yeah? Define. No noise, please. In it. And value.
It's not in it, it's in it.
Okay. Value left, yeah? And then right. Yeah, this is the value for the node. And left points to the left node. And right points to the right node. Look, what does this mean? Anyway, look, this parent can point to the left and right. And for kids, it doesn't usually know which parent, right? But there's a way you can keep tracking of this, you know, where it comes from using this depth search. Yeah, by passing down the parent value, okay? DAG, okay? So, what have we talked about yesterday? We talked about this, yeah, from 0, look, 1, 2, 3, and then here. Is this a DAG? Is this a DAG? Come on, is this a cycle? Is this a cycle? Look at the arrows. Is this a cycle?
Yeah.
Is this a cycle? No, come on, you go this, but you cannot go back, right? So this is a DAG, right? Directed cyclic graph. It doesn't have a cyclic. Look at the arrow. Yeah, 0 can go to 2, but 2 can not go back to 0. Okay. So can you find the paths between all the paths between 0 to 3?
0, 1, 2, 3, 0, 2, 3.
Well done. Only 2. Okay. So what have we used yesterday to implement the algorithm?
Depth of search.
Yeah, we talked about the depth of search.
Today we talk about
recursion. Yeah,
breadth of search.
Recursion.
Q. And today we're going to talk about
Breadth of search and Q. In Python, DQ. What's DQ mean?
Double ended Q.
So it means a queue which you can have the pop the both sides, pop left, pop. Append left, append. Okay? So it's a queue. You can do perform operation, push and pop operation on the both sides of the queue. Okay, that's DQ. Can you tell me what's the DQ what's the
Why does the other ones need?
Okay, what's the breadth of search of this? Breadth of search
1, 2, 3, 5, 6, 4, 7.
Okay, level by level.
But it needs circles.
Okay,
Like the
that's fine.
wonders.
Yeah, okay.
Hey.
Okay, so let's implement this. Okay, define all paths. Source. No, let me just have a graph. Okay, that's it. First of all, we need to find out the n. N is length of the graph. Okay, graph is defined as the adjacent link list. Okay, adjacent link list. -1, adjacent. That we are finding the source. We are finding all the paths between 0 to n -1. Okay, so actually, yeah, let's just do this to n -1. So adjacent linked list. So G is adjacent linked list. What does it mean? The first element G0. G0. What's G0 mean? It means look, Eric. So what's the adjacent list? Okay, 0 to 1. Let's do this again. Okay, to 3. What's the adjacent list? How to represent this adjacent list of this graph? G0. Where is 0 connected to? Come on.
1, 2.
1 and 2. Okay. And what's G1? Look, G1. What's 1 connected to?
1.
Sorry, 1 connected to what?
2.
2. That's it. Okay. And what's G2 connected to?
3.
Yeah. And that's
Hey,
it.
where's the arrow on?
And G3 is the
where's
error.
the arrow on 2 to 3?
Sorry.
There isn't a pointy thing. Yeah.
Okay. G3 points to nothing, so it's an empty list. Okay. So look. So this is adjacent list G. Okay. Yeah. You see, the key, the 0, 1, 2 is the node, and then it points to a list which has the nodes that it connects to. It has these directions. Okay. So G, and then in order to implement the as we said, we use the DQ. Yeah. Let's give Q equals DQ. So what parameters do we need to? We need to store the number of the path, the current path, and we also need to store the current node. Okay, so at the beginning, what do we put in it? What do we put in the array? What's the current node? What we put it in the tuple, yeah? Tuple, remember the tuple. What the tuple is contains the list of elements. Yeah. What's the difference between this list and tuple?
I think one of them is immutable.
Immutable. Tuple is immutable, means we can't change it. Okay, so tuple. Eric, what's the first element to put? Where do we start searching the path from?
From the beginning.
0, right? And then what's the path?
N minus 1.
No. The path will be at the beginning will be 0, right? So it's a list of this is the current path. This is the source. So the tuple will be current node, okay, and then the path. Okay, so we just use the path. Path is a list of list of nodes with integer, and then this is the integer. Okay, int, list of int. Q. Okay. So we have the initial node. So what do we do next? We need to have the answer variable to store all the elements, all the paths, right? And then while what? Remember we talk about this breadth search. We need to find out if they are.
While Q.
What does it mean of while Q?
Well, there's elements in the queue.
Why there is something in the queue, okay?
Yeah.
And then we need to take the elements in the front of the queue, which is the current node. And then that's a tuple, yeah? So we can use the comma. What's this? Path, yeah? Path equals Q dot what? We want to take the left. Pop what?
Left.
We want to take, what's the difference between pop and pop left?
Pop left is, not sure.
Pop left, which direction? Pop left, okay. So we have a Q.
At the beginning.
Okay, look, 1, 2, 3. Pop left, what happened?
1 is gone.
1 is gone. Okay, if pop, what happened?
3 is gone.
Well done, yeah, you see? There is no pop right, okay? It's pop left and pop, okay? Correct? Yeah? Because the list, by default, when you do a pop from the list, it's from the right hand side, yeah?
Why?
Just by default, the list, here is the list, yeah? The list is like a stack, yeah? 1, 2, 3. So
Then
look,
why-
what does it mean?
Then why can't you turn the other side?
Good point. By default, this is 1, 2, 3. The list is actually like that. Okay.
Yeah. But
1, 2,
that's
3.
stack. Yeah.
A stack. So when you pop,
Yeah,
you
so
take it
why
out.
can't you turn the other side?
Good point. No. That's just by the definition we're using this. If you want to do this, you can do this. If you want to take take the first element out of the list. What happens? Remember, we can still use pop, but we have to give a parameter what? We want to take this out. Pop it. What happened? A dot what?
It'll end.
No. We want to take this out. Pop what? Remember? There's a value I put here.
0.
0, well then pop 0. Okay. If you don't put a parameter, you take the last element out. Okay.
Or left.
No. Left, pop left is only applied to DQ, but a list doesn't have a pop left. Okay? Yeah, it's
Why?
different object. Yeah, different object. Do you understand? Yeah. Like you can ride a horse. The horse has the right. Yeah, right method. Right. But a car doesn't have a right. Car will have another method called drive. You see, this is object oriented. Different object have different methods. No. This is the same. That's why I talk about this list and DQ. They are different objects. That's why they have different. They are similar, but they have different kind of methods. Got it? It's like horse. You can only ride a horse, and you can only drive a car. You cannot.
You can walk a horse.
Yeah. You cannot drive a horse, and you cannot ride a car. Okay. Okay. So okay. Coming back to the subject. Coming back to the subject, we got the current node. We got a path, and then we need to check if current node equals what. If current node equals the target, which is target? N minus 1, okay? 0 from to n minus 1. And then,
to say that.
Okay, n minus 1, then we answer dot append what? We need to put this current what? Come on. What's the answer? Answer is the stores the list of paths. And what's the what should we append? What should we append?
We should append.
What's your append? Come on.
Current path.
Yeah, path. Yeah, path. Current path. And then what happened? If we do this, and then what should we do? What should we do? What should we do? What should we do next?
What should
we do next?
Current
node. What are the next node for next node? Yeah, next node in what?
G.
G what?
Current node.
Yeah, G current node. Yeah, we know this already. And then what should we do next? We should do what? We find the next node, so we know where it goes to next. So we want to build a path, right? So can you tell me what to write? What append? Q. Yeah, we append into the list into the queue. Append. That's a tuple. Yeah, the first node is the next node, which is what? Next node. And the path will be updated into what? Path plus a next node, right? We want to give a next node. This is the new path, right? Got it? Yeah. And there's one thing missing. Where?
Two things missing.
So it's least simpler than the depth search. Remember, which one is simpler? The depth search we implement the recursion. We need to push and pop the path, right? But for now, we don't need in the breadth search we just update the path here. We just push the new path into the queue. That's why we don't need to push and pop, right? In the depth search, we need to push the new node into the current path, and then we call a current path. Call a depth search. After we finish the depth search, we need to pop the node from the current path to restore it. Yeah, to restore the state where it was. But for this one, the breadth search, we just we just push the node, yeah, the node, and we take it out from the queue until, and we expand the next node, which is the next edges, yeah, until we find the destination, which is n-1. What's the time complexity? This is a bit tricky because in the worst cases, what? It's a directly acyclic link, a cyclic graph. Yeah? So what does it mean? If you look at 0, if there are, let's say that if there are 5 nodes, okay? 0 can go to 1, 2, 3, 4. Yeah, 1, 2, 3, 4. Okay? Yeah? 1 can go to what? 1 can go to
Nothing.
2, 3, 4. Okay? Let's do this graph. 2, 3, 4. And 2 can go to what? 3, 4. 3 can go to 4, yeah? So every node can go to the node which have a larger value. to satisfy directed acyclic link. Yeah. So how many nodes? How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 edges. There are 5 nodes, 10 edges. Yeah.
Each one has 2.
No, look, 0, 0, 1, 2, 4 plus 1, 2, 3, 7. So it's 4 plus 7 plus 2 plus 1. Yeah, plus 1. Okay, so that's 10 edges. So there are n. When n is what? And when n is 5, is 10 edges. So when n is 6 is what? 15 edges, right? Is it right? We can do this. We can do this again. Maybe do a 6. 0 to. Let's write it in a tree. Okay, 0, 1, 2, 3, 4, 5. Okay, 1 could be 1, 2, 3, 4. Yeah. 2, 3, 4, 5. Yeah. Okay, so it's actually more than that, right? Look. Okay, so actually this is not entirely correct. Let's write it again. Just 4 edges. 0 can go to 1, 2, 3. 1 can go to 2, 3. 2 can go to 3. Yeah, 2 can go to what? 2 can go to 3. Okay? So each node can go to the nodes that have a larger value. So by series, okay? By series, it has if that node, they will have 2 n minus 1. Okay, roughly. Okay, let's say if it's the same, n is 4. 4 minus 1 is 3. 2 to the power of 3 is 8. 1, 2, 3, 4, 5, 6, 8. Okay, 6, 7. Okay, roughly. So that's the number of edges, and to build each one roughly, it needs the n, right? O(n) time. So the time complexity is O(n) times 2 to the power of n minus 1. Is it? 2 to the power of n minus 1. 2 to the power of n, right? Because 2n minus 1 times 2, okay? 2 to the power of n. 2 to the power of n. N is 4. Okay. So the space complexity is the same as the time complexity, because you will need, and in the worst cases, you will need answer to store all the paths. Yeah, to store all the paths. Okay. Any questions so far? Any questions? Any questions so far?
No.
Any questions?
No.
Yeah. Okay, I'm going to erase.
Right.
Okay, I'm going to erase what? Here, this bit. This is the top bit, and the next. Okay, two things here.
Oh.
Can somebody help me?
No.
So you tell me what to do here.
Just.
What do we do?
Node.
What do we want to do?
Current node.
So
Path.
current node. So what current node and path what? This is
Equals
equals what?
Q dot pop.
Yeah. So that because they're tuple, each one you pop 2 elements there. Q dot pop that right now. The first thing of backward search is to pop it from the front of Q. Okay. And then here we don't want to build what?
Q dot
Append.
append.
What's
Next
the
node. Current path. That's next node. Sorry.
next node and then current path? Yeah. Load path. Yeah. Plus square. Okay. It's a list plus another list. Yeah. Next node. Why we need a bracket here? Look, if this is a list 1, 2, 3. Yeah, we want to add another 4 to it. Alright? Ryan, this is a list. We want to add it. So we can do this A plus what? A plus what? Bracket 4. Okay? Got it? Look. Does it make sense? This is a list, everyone. Look. I want to add another element to it. Yeah? Got it? Or you can look, normally we can do this A dot append, right? But A dot append doesn't return anything. Yeah, A dot append doesn't return anything. Instead, you will push the 4 into this. You will change the value of A. Another way is to A dot. There's another keyword called extend. Okay, extend, and then you can give another list. Okay, 4, 5, something like that. Then it will become. Okay, can you tell me what's next? A dot extend 4, 5. What does it become? What's A become?
1, 2, 3, 4, 5.
Well done. Okay, or you can use this A plus 4, 5. Okay, yeah. You can concatenate two lists 1, 2, 3, 4, 5, and then that will become 1, 2, 3, 4, 5. Got it? Okay, that's it for today. Good job.
Bye.
Bye bye.